Hello. If you've clicked on this video, you're probably wondering, like the thumbnail says, how can I apply periodic boundary condition manually? Because to be honest, there is no tool out there that can help you do this easily, especially within ABAQUS, without having to resort to a plugin of some kind. And so this is what I want to show you in this video. How can you apply periodic boundary condition manually? If you've been around the PBC modeling community, you know you need to know where the corner nodes are, you need to know what the internal nodes are, you need to give numbers to these nodes, you need to link the internal nodes kinematically, you need to develop canonical equations that tells ABAQUS what's happening both in the x and y direction this way. So you know all this, and the theory, you've formulated it up to this point. How do I then move from here to get this content into ABAQUS? At the end, you want to generate results that look like this, which is basically a uniaxial deformation along the x-axis for this composite material. So sit back and relax as we get into it. Hello everyone, welcome to CM Videos, a YouTube channel where we help you get started with modeling. And if you're already down the modeling route, we also help you curate effective finite element solutions. This video is dedicated to helping you apply manually periodic boundary conditions in ABAQUS. You would also have seen previous video that I made where I introduced the theory of periodic boundary conditions. There's also another video where I show how you can also do this automatically. Again, please check on the cards. The domain that we're going to be using would be a unidirectional composite, a representative volume element of a unidirectional composite, and the material would be a glass fiber reinforced plastic unidirectional composite with the properties of the fiber and the metrics given. I've also done a video which I put on the card where I showed you how you can actually start creating this representative volume element. The way we're going to go about it is to use a script. I've regenerated this random distribution of the fibers using a Monte Carlo implementation, which is an algorithm that I've developed for doing this automatically. But the key thing you need to bear in mind here is that these circles, which represent the fibers, their positions are presented there. Like I said, we're going to be creating from this to the RV of the unidirectional composites into this ABAQUS version using a Python script. The Python script will be available for you to pick up in the link below. So the case studies that we'll be studying here would be first a tensile deformation along the x-axis. The case 2 would be along the y-axis in compression, and case 3 will be a shear deformation. The boundary condition for uniaxial x-axis tension. What about uniaxial compression in the y-axis? Now the last bit is the shear deformations, and it's basically a simple shear scenario. So now let's move into ABAQUS and begin the manual implementation of the periodic boundary condition. So here we are in ABAQUS. We're going to implement this manually, and like I said, we're going to use a script. So if I show you a bit of the script, so this is a script that we are going to use. Again, I've automatically created this using this algorithm that comes with my Monte Carlo process. So it basically helps write out the script for me. Then the most important thing you need to know here is this information. So this is kind of where the fibers are created. The domain that we are using is somewhere created at the top. Okay, so I'm just going to copy that. So if I copy it, then come back to ABAQUS, paste it here. So if we paste it in that environment, so obviously it will run through and then it will create the domain. So this makes life sort of easy for me. So we're not going to do much about that. So let's just look at what we have here. So the fiber, I've left it as a blank template so that you can put in which properties you want to use. So the elastic properties of the fiber for E glass is 73 gigapascal and a Poisson ratio of 0.2. Now for the metrics, again, it's an empty blanket for you to put whatever you want. So 1.308 e to the power 9 and 0.4 for polypropylene, which is what we're using. The plastic properties for the polypropylene is 4 e to the power 6 and 0.0 that. So again, you can put in some damage model as well if you want to do that, but we're just using a simple elastic plastic model here. Now the fiber section, we link it to the fiber, and the matrix section is already linked. So we now open this RVE 2D to do the section assignment. So I select that. So this will be my matrix region. Then I select every other thing. They select the matrix, leaving the fiber, and make this my fiber region. Okay, so I changed to fiber. So this is fine. So we've got the information that we need. So now the next thing we need to do is to apply our mesh. So if you double click on the mesh, okay, so let's try something like 30, because we want just very few boundaries, very few nodes. Okay, so we only want a very few nodes so that we can kinematically track this. Um, um, yeah, so let's see if what that will give us. So if we then, I'm going to use a triangular element shape to mesh this. Okay, and then we mesh. What I would like to do next is let's create a set. Okay, so I'm going to call this my X front set based on node continuous. So I'm going to select its edge, future edge. Okay, maybe let's do it individually. So we just select the internal ones. So these are the internal ones that we're interested. So we click done. So we do the same with X back. So we get the corner nodes now. So I'm going to call this the corner nodes based on nodes. So again, press down shift and select all the corner nodes individually. The next thing we need to do is obviously we need to know what these node positions are, what the node numbers are, so that we can then go ahead and use them for that. So the way to go about this is we'll go to view. Okay, maybe not, maybe view, part display option, mesh, show node levels. Okay, so we can see the node levels. So what we are going to do to find a way to extract them, we're going to query based on sets. Okay, so X front, so let's highlight X front, so which are those node levels in the front. So click done. Now what you will notice here is that it gives us a list of the information that we want, a list of the information that we want. So we go to sets. Okay, so double click on that. So first thing we need to do here is, okay, node. So I'll call it node 20, continue. So this is this, done. So the next one is node 6, continue, which is that. So the next one is node 66, which is that. So we're going to run all the way through, so we create all the nodes. So I'm going to speed this up so that we can get all the nodes created. Okay, so those are all done. So we've got all the nodes selected. If I just select them, so none of them is missing. Everything is selected. So that's one part of the job done. So we've labeled the nodes. The next thing we need to do is, okay, so we'll just go work our way down this route. So the assembly instances are all created. So loading step. So let's call this a loading step. Okay, so we've got a loading step created. So this is fine. Now the next thing is we need to create the constraints. Okay, so if you click the constraints, so remember the constraints, we are going to use a star equation. So, and we're going to have to link it one after the other as we go our way around. So if we again show back the meshing, and then within this module, if I show the node levels, okay, in the assembly module, so we've got the node levels. So if we look at the parts, the materials, okay, so we have to then do the coupling. So we start with this coupled to that, and then we work our way around the model. So let's see equation 1. So let's just call that equation 1. And I'm going to go my 1 in the x direction. Star equation, continue. So if I open this up to show you what we're trying to do. So basically, we're applying the star equation. So the coefficient here is 1. The content that we're looking for is node 20. So we look for node 20 here. Okay. And degree of freedom for it is 1 in the x direction. Then minus 1, the reference point for node 1. So this goes to the back, node 20 connected to node 17. So we go to node 17. So we look for where node 17 is. Okay. Degree of freedom 1 again. Now minus 1. Now what is it connected to? This, and node 5 and node 4. So look at node 5. Degree of freedom 1 again. So global. So we have to tell it. And then 1 finally, node degree of freedom node 4. Okay, degree of freedom 1 and then global. So let's work out, let's think about what we have. So displacement for node 20 minus displacement for node 7 is equal to displacement for node 5 minus displacement for node 4, which is in canonical equation basically node 20 minus node displacement for node 7 minus displacement for node 5 plus displacement for node 4 equal to 0 in the x direction. Okay, so that's our equation 1 in the x direction. So what I'm going to do with this is I'm going to copy and make the same equation 1 but in the y direction, because we need to tell it what it needs to do in the y direction. So the only thing we need to do here is to change all of this to 2. So that forms our equation 1, which makes a canonical linking between this and that. Equation y does the same canonical linking between that and that. So we've got those two. So now I'll create equation 2x. Okay, but this time around, if I open that up, I'm going to move to node 6 and node 3. Node 6 and node 3. So let's change this to node 6, linking to node 3. Okay, in the one direction. So we're still referencing those bays, so there's no problem with that. So we look at that, so see what we've done. So we've linked this node to that node. You can see that the color is different, this node to that node. So I'll create a copy of that and do it in the y direction as well. So the only thing I need to do when I open that up is the degree of freedom would be in the y direction. Okay, so we have information about what happens with this linking. Right, so we're going to do the same for all of them, and when we finish that, then I'll come back and talk about this. So let's just speed up the video. Okay, so we have done all the canonical linking, star equation linking for all the x fronts, and we've linked it to the base here. So all the x front, you can see they are selected and they are linked to the base there. So the next thing we need to do is for the, okay, so we need to do the same thing for 8 and 9. So let's just do that. So I'm going to do 7, equation 7x. So which means, so we're looking at equation 8, node 8 with node 9 linked, node 8 and node 9. Okay, so we can see they are selected and they are there. So I'll just create the Y version of it, which basically means I just need to go in here and do this, change it to 2 degrees of freedom. So we need to tell for every node this canonical linking, tell ABAQUS what to do in terms of X and Y, and we are doing this manually. This can be automated, this process can be automated, but I'm just trying to show you how you can do this quickly, you know, in a manual way, especially for those of you that are interested in this. Again, if you are finding this video of value to you, please smash the like button and put a comment. Tell me what you think about this process, what we are doing. Do you think it is too laborious? Do you think it's something that you would like to do? Do you think there's a better way that you can actually do this? So far I haven't found a way to do this, but do give me feedback of what you know, whether you're finding any ton of value in what we are trying to do. So the next thing we need to do next is to think about the Y direction, okay, the Y axis. So we need to tell the model what happens in the Y direction. So we're going to start with node 28 and node 18, I believe, node 28 and node 18, but we're going to kinematically link it with what's happening at 9 and 4. 9 and 4. So we're going to copy the, you know, let's say I'm going to call this my equation 8 in the X direction, okay. Double click on that. So we need to change the references. So we're looking at node 8 to node 8, sorry, 18 to 8. So 18, so node 28, I believe. So node 28 to node 18. So let's find where node 18 is. Okay, so node 28 linked to node 18, and then in the Y direction we are linking node 9 to node 4. So node 9 links to node 4. Yes, so node 9 links to node 4. So we've got 28, 18, 9 and 4. So that's the X direction of that. So we'll do the same for the Y direction of it. Okay, and what does that mean? It basically means change the degrees of freedom into the Y direction. So finally we will create the equation 9x, and equation 9x will be based on 27 and 19. So 27 and node 19. Okay, and it's still linked, kinematically linked to 9 and 4. So this is fine. So we've got that. So we create the Y version of it. So we've got the Y version of it. All right. So what would the Y version of it means? It means we change these degrees of freedom to 2. So if I select all of them, you could see that we have provided kinematical linking, you know, a periodic boundary condition information for all the surrounding boundary nodes for this model. And it becomes what I like to describe as a BBC aware domain. So we are happy with that, so we stop there. Now think about the boundary conditions. So what I'm going to basically do here is, if I, you know, maybe if I rename this and call it X case 1, which is extension, but at the boundary condition, so we double click here. So remember, our boundary condition will have to be based on initial. So I'm going to say X back roller. So we want to put a roller support at the back, but we're not going to select all of them. Remember, we only said you have to select 2 nodes. So you select that node and select this node. So this will be X back with a roller support on initial boundary condition. Select the region, so we want that node. I'll press down shift and then we'll select this other node too. Okay, so both of them are selected. So we want to constrain it in the one direction, okay, to prevent movement in that direction. We need to do Y base roller. Okay, select that node, press down shift and select the corresponding node on the other face, and then we pick up the Y direction. So we've got that, and then our X tension load would be a loading history displacement based. So I'll pick up that. So select that corner because this is where we want to apply our load, and then click done. So now I want it to be a 10 micron displacement. So you find that there. So I could then call my case. So that's done, and then I can submit that, just make sure, and so on and so forth. So job done, completed. So let's look at the result quickly to make sure that everything is fine. Okay, so that looks okay. We'll come back to it later on. So the next thing we want to do now is let's create a second case. So this will be copy. The hardest part of this is really creating the boundary conditions, the kinematic linking. So in this second case, our boundary condition will be different. So X back will be okay. So the X back algorithm will be fine. So what we need to change here, so if I rename that, so if I rename this, so this will be Y compression. Okay, so my Y compression load would have to be different from this. So I'm going to pick a different region, which is this region. Okay, and then the loading has to be in the negative direction. Okay, right, so not necessarily what we're looking for. So just the loading is not in the X direction, but rather in the Y direction. Okay, so this looks fine. So we've got our load acting down this way. So I'm going to do that and say case simulation. Okay, so we'll submit that to run, and then the final bit is case. So we'll create a copy, and this will be case 3, and that will be XY shear. XY shear. Now again, the boundary condition that we created before will be adopted as usual. The only thing we need to do is we need to think about, so this X back roller, so this X back roller which we had before was only in the X direction. So I'm going to rename it and call it X back fixed. Okay, and open it up so it will be fixed in the X and Y direction because we're using simple shear. Y base roller would have to be suppressed. Y compression will have to be suppressed as well because it will not be applicable. So what we need to do is X front roller, and it will be an initial boundary condition, displacement again. So we'll pick that corner, press down shift and select the next corner here, which is that. Okay, so we've got the two of them selected. Okay, and then it will be constrained in the one direction. Okay, that's fine. And then we now have XY shear. XY shear. It will be a loading step, and then we apply it on this corner node. So this will be in the Y direction. I mean, we could use the same 10. I mean, let's double it and use a 20% shear. Shear, normally you need a lot of displacement to incorporate shear. So if we then do, so this will be case 3, XY shear simulation. And then we can then submit that to run. Okay, so if we go back and see the results for extension, now with periodic boundary condition. So just to really test if everything is fine. So if we okay, so the first thing to do is with periodic boundary condition, I'll increase the the scaling factor to 2 just to make sure that we have, or maybe 4. Do we have the periodicity? Okay, so there's a periodicity in all direction. So I'll look at the plastic strain. Okay, the plastic strain is fine. So you do get this periodicity and periodicity in the front. Clearly, we haven't deformed this model properly. So let me just take out some of this information. So set this all off, show triad and legend. So I want the legend to be about 20. Okay, yeah, so this is fine. So the back and the top, they are all periodic, so that looks good. I mean, you can try a little bit more. Okay, maybe that's too much, so let's do 6. Okay, so this looks fine. Again, if I go back my viewport, I don't want this legend to show the bounding box. All right, so so we need to know what the legend is about. So the legend is fine, title is bounding box, I don't want. So yeah, so there's a bit of periodicity: back displacement mirrored, front displacement, base displacement mirrored, top displacement. So that's good, that's what we want. So let's go back and look at what's happening in the y direction. So if you look at the results in the y, again, we want to make sure we have periodicity incorporated. So there's too much deformation there, so let's do 3. Okay, so again, if I go back to my plastic strain argument, okay, so there's a one-step implementation for here between the deformed and undeformed, and again you see periodicity: back periodically deformed, front, base, and top. Fine. So let's do the final case, which is the shear case. Again, if you're finding this content really beneficial, please do smash the like button or leave a comment of what you feel about what is going on here. So there's too much deformation here, so what we're going to do is let's do auto compute. Okay, so this is fine. So again, what does that show us? It shows us that we have our periodicity as well: the back periodically with front, the base periodically with the bottom, and then what does our plastic strain shows. Okay, so you see the principle here of how you can imply periodic boundary condition. Of course, our mesh is very coarse, it's not very properly not fine, but this is because we're doing this in a manual way. But if you want to do this, obviously this is a real possibility. If you're desperate to get periodic boundary condition incorporated in your model, you then obviously need to add more elements on the sides and on the base, more seeds, and then basically go through the process in the way that I've shown you in this video, and that would be the way to go about it. All right, so one is being so why not let's just increase the scale to maybe 1, 2, because the shear is being pulled a lot in that corner. So it doesn't look good, but this is the idea of what we're looking to achieve with this video. So if this is the kind of content that you like and you're finding value in these videos, please do subscribe to this channel. Leave me a comment of what you think about this video. Do you think this is the way to go about this? Do you think there's a better way to do it? Is there anything that you would like me to make a video on? And whatever it is, please do give me some feedback. And if you're finding joy, you're liking this content, please smash the like button. And if you look at the card on the left and the right, you will see links to how the theory of periodic boundary condition, the previous video that I've made, and how you can do this automatically. Okay, automatically. So please watch out for those videos, and hopefully you find them useful. Thank you for your interest in this channel. I'll see you in the next video. Bye bye.